Okay, so we're going to look at the Argand diagram. So the Argand diagram is kind of like the complex equivalent of our Cartesian plane, our xy plane that we're used to for our kind of standard numbers up to our real numbers. And when we're looking at our Argand diagram, we can think of it as being like an extension of our number line. So if we think of this real axis here being our number line, what we're doing is we're extending that kind of upwards and downwards to include those imaginary parts into it, so to include our imaginary numbers there. So by going up the way, we're adding positive imaginary parts. By going down the way, we're getting negative imaginary parts. So our real axis corresponds with the x-axis on our normal Cartesian plane, and the imaginary axis corresponds with the y-axis. Okay, and we can see that in the points that we have there. 2 plus 3i, I go across, 2, I go up 3i, minus 2 plus 5i, I go across minus 2 and up 5i. So we can see you're plotting them in a similar way to what we're used to with our xy coordinates, the only difference being here that the first part is the real part, the second part's the imaginary part, and they're presented to us kind of as one kind of expression, but we're going to be plotting them taking those two separate parts into consideration. So a particular thing that's important about our complex numbers then and plotting them is this idea of the modulus. And we've seen this modulus before with this notation of the two lines either side. But in terms of complex numbers, our modulus is the distance from the origin to a particular point in the complex plane. And really, if we look at it just a little bit here, if I said that z was a plus bi, this distance here would be a distance of b, this distance here would be a distance of a, and we can see that what we've created is a right angled triangle, and we use this letter or for the modulus. And from Pythagoras, we could rewrite that or is equal to a squared plus b squared, so or itself must be the square root of a squared plus b squared. And that's really where our kind of notation or our formula for modulus comes from. And you'll notice as well, when we look at it, we're taking a squared, the real part, and b squared, that imaginary part there, but we're not including the I in those calculations, because if you include the I, that's going to throw your answer off somewhat from what it actually should be. So looking then at this first few examples here, so let's look at the first one. It's the square root of 3 squared plus minus 4 squared, which is going to be 9 plus 16, which is root 25, which is of course 5. The same thing goes with the second one, 2 squared plus 1 squared, which is 4 plus 1, which is root 5. And again, you'll get into kind of a habit with these ones because you end up having to practice these quite frequently with all of the different calculations that we have in our complex numbers questions. So particularly say finding polar form later in this chapter. So just making sure here as well that if you are using your calculator, that you're just using brackets when you're inputting things like square roots of a root, or squaring root 3 there in the last one, that we input and use our brackets for that one without just, instead of just kind of typing it in, because we run the risk sometimes then of it just kind of squaring it with kind of getting rid of things or not squaring it out properly. And we just want to kind of make sure that we give ourselves the best chance, particularly if we have a question where it's maybe 2 root 3 or 4 root 3 or something like that, that we want to include that 4 in the squared part as well. So looking at these questions here, the only slight differences that we have compared to the previous ones are in these last two parts. And all that we would need to do for those two is we would need to simplify the terms that we have inside the brackets before we compute the modulus. So say we look at the last section there, if we wanted to compute the modulus of this, we would have to do out the multiplication first. So that's going to give me 6 plus I plus 48i plus 8i squared, which gives me 6 plus 49i minus 8, which gives me minus 2 plus 49i. And then I could compute my modulus of that as per normal, I suppose. So following through, and I would get an answer here of 4, and then 49 squared is 49 by 49, which is 2401, and I get square root of 2405, and we can check if that goes down any further using our calculator, and it only goes down to give us a decimal, so we don't really want a decimal, we'd prefer to leave it in surd form. So that's the only thing to be careful of there, is if you have a modulus like that, that you compute what's inside the modulus before finding the modulus of that kind of calculation, of that expression. So looking then a little bit at these exam questions here, we'll just kind of have a quick look. Say for the first one here, show that z minus iz is equal to 8 minus 4I. So let's first of all work out what iz would be. So that's just taking z and multiplying across by I. So that gives me 6I plus 2I squared, which gives me minus 2 plus 6I. Then if we work out z minus iz, 6 plus 2I minus 2 plus 6I. Being careful here as well, because we're subtracting all of that, we should use our brackets just to keep it clear for ourselves. We get 8 minus 4I as required in the question there. Now we're asked to show that the modulus of z squared plus the modulus of iz squared is equal to the modulus of z minus iz all squared. So we're going to compute those modulus first, and then we're going to square our answers. So let's get the modulus of z first of all. So looking at the question, that's going to be 6 squared plus 2 squared, which is the square root of 36, plus 4, which is the square root of 40. The modulus of iz then is going to be minus 2 squared plus 6 squared, which gives us actually the same answer as we've had, 36 square root of 40. And then if we find the modulus of z minus iz, which we know from the previous part, and even if we hadn't computed the previous part, we still could use it for this part, gives me 64 plus 16, which gives me an answer of root 80. So now we want to look and see, is the modulus of z squared plus the modulus of iz squared the same as the modulus of z minus iz all squared? So let's have a look. We're doing root 40 squared plus root 40 squared equals root 80 squared. And let's see if that's correct. 40 plus 40 equals 80. 80 does in fact equal 80. So we're happy that we're correct with those answers there, and we've shown that that is in fact true and is in fact correct. So with our modulus there, as we've said, it's important that you work out those individual calculations, if there are any, between those two lines for your modulus before you compute that modulus, before you go to the square root part. We're going to move on a little bit then and look at the last little section with Argand diagrams, and this is transformations. And the transformations can take a little bit of thinking and a little bit of kind of extra looking at, and there's something we're going to look at as well when we get into kind of enlargements and transformations in geometry later, but we're just touching on it here as it relates to complex numbers, and it's something that's covered in our book as well, maybe in extra detail as well. But just as a quick kind of crash course, I suppose, if we are multiplying a complex number by a real number, if we multiply by a number that has a modulus of 1, and remember in this sense we're looking at modulus in the same sense we looked at it in algebra, we just mean a positive value. If I take the magnitude of it, I suppose, so if I'm multiplying by something that's bigger than 1, it could be positive or it could be negative. If I'm multiplying by something that's bigger than 1, I'm going to be enlarging or stretching the complex number a factor of k away from the origin. So say over here, if I have my complex number z and I multiply by 2, I have stretched my complex number twice as far from the origin as it was originally. If we multiply by something that is smaller than 1, so say a fraction, what we end up with then is we end up with our complex number being half as far from the origin. Or if we did a quarter, it would be a quarter as far from the origin. The modulus would decrease by a factor of k. So not decrease by a half, but it would be half as far. If we multiply by a negative real number, then we reflect the opposite direction. So we take, say for this example here, where it's minus a half z, we have multiplied z, which is over here, by a negative number, so we're reflecting the opposite direction, and we've also multiplied it by a half, which is smaller than 1, obviously, so that has resulted in it being closer to the origin. We've reduced the distance from the origin for that one there. Okay, looking then at adding and subtracting. When we add or subtract complex numbers, we can consider that to kind of be a translation of sorts. We're moving the complex number a particular direction. And when we add two complex numbers together, the result will be the diagonal of a parallelogram that we construct between the 2 points we're talking about. So to kind of see what I mean by that, if we have 2 points Z1 and Z2 to here, and we added them together, we would end up with Z1 plus Z2, and we can see that that point is in the corner of the parallelogram that happens if we were to join up all 4 of those points, including the origin. Okay, so always important to know that if you add the 2 of them, it'll end up kind of between them in the corner of a parallelogram, a little bit further on most of the time as well. So Z1 plus Z2 is a translation where we would move, if we start at Z1, say this is A plus B I, and this is C plus DI, if we add them together, we have moved A plus C in the real axis and B plus D in the imaginary axis. Okay, we've moved in those certain ways there. The same thing happens then when we take away the imaginary, take away the 2 numbers from each other. Okay, we have that same translation in the real axis and in the imaginary axis. If we're multiplying by I and minus I, if we multiply by I, that's going to rotate our complex number 90 degrees anti-clockwise. So we end up with our new complex number being at an angle of 90 degrees with the previous one through the origin. Okay, so taking this one here, we've rotated it 90 degrees anti-clockwise. If we multiply by I squared, we've rotated it 180 degrees. If we rotate it by I cubed, it would be 270 degrees, and so on and so forth. So powers of I just result in large rotations. If we multiply it by minus I, it would rotate it clockwise, the opposite direction. Okay, and multiplying and dividing by complex numbers, so by the whole complex number, is going to result in a combination of these transformations that we've looked at. So we're going to end up with different varieties of these different transformations that we have been looking at there. And it just depends on what the complex number is that we have multiplied by, I suppose. So let's just look at this example here then. So we're looking at Z1 being 2 plus 3i, Z2 being 1 plus 2i, and Z3 being minus 2 plus 1i. And we have this A as well being 3. And we're asked to plot Z1, Z2, and Z3. So let's just plot those first. So using our Argand diagram, we go across to 2, we go up to 3i, and that's going to put it about here for Z1. Z2 then is going to be 1 plus 2i. So let's have a look at this one. That's going to put it about here. And Z3 is minus 2 plus I, which is going to put it around about here for Z3. Now looking at the next part, we're asked to evaluate AZ1, AZ2, and AZ3. So let's do A. A is 3, so we're multiplying each of our complex numbers by 3. So that gives me 6 plus 9i for AZ1. So let's go to that point, and I can plot it here. That's AZ1. I can do AZ2, so multiply across by 3 again, 3 plus 6i. And I can again plot that one for ourselves. And that gives me AZ2. And then again for Z3, the same thing happening again. So we get minus 6 plus 3i, go across to minus 6 up to 3i. And that gives me my 3Z3 there. Okay, so we've plotted in all those numbers. They've asked us to describe the transformation that is multiplication by A. A is a real number, and A is going to be bigger than 1. We know A is bigger than 1, so it's a positive real number as well, and it is bigger than 1. So that results in a stretching or enlargement. And we can say a factor of k of 3 or of A from the origin. So we've stretched it a factor of A from the origin. So A times further from the origin. For part 4, we're asked to plot Z1i and Z2i squared. We can work out what those actual values are for ourselves, just to save ourselves from kind of eyeballing it, I suppose. So we're multiplying Z1 by I, because we 2i plus 3i squared, which will work out as minus 3 plus 2i. So let's slot that one in here. It's just a little bit above one of our previous answers. So that's Z1i. And then Z2 I squared. So I squared is the same as multiplying by minus 1. So that'll give me minus 1 minus 2i. And again, I can slot that one in as Z2i squared. Okay, describing the transformations, those are rotations. Those are going to be rotations. So a rotation of 90 degrees and of 180 degrees. Then if we want to plot Z1 plus Z2, we just have to work out what that value is going to be for ourselves here. So nice and simple, 2 plus 3i plus 1 plus 2i, we get 3 plus 5i. We can plot that in for ourselves. Z1 plus Z2. Okay. So our scale there quite small, so maybe just harder to see for ourselves across the whole question there. But we get the kind of idea of plotting all of these points. Now the exam questions kind of require us to really have a kind of understanding of what we're doing, I suppose, at each step here. So we're just going to talk through these few ones here. So a complex number z has modulus greater than 1. The three numbers z, z squared and z cubed are shown on the Argand diagram. One of them lies on the imaginary axis as shown. Label the points on the diagram to show which point corresponds to which number. So something to note here with our modulus is as we square our complex number, our modulus tends to get bigger. Okay, as we square the complex numbers, our modulus is going to get bigger. They're going to get further and further away from the origin. So we can think of if we're squaring any of those kind of complex numbers that we have, they're going to end up being further and further away from the origin. So looking at the options that we have here, I suppose, if we start with z, that's going to be the one that's closest to the origin, which would be this one here. Then the next furthest one might be this one here, and then this could be z cubed up the top here. And the reasoning being that as we square or cube the complex number, our modulus is then getting bigger. Okay, looking then at the 2014 sample paper option, we have four complex numbers here, Z1, IZ1, Z3 and Z4. The same scale is used on both axes, and we're asked to represent or identify which number is which by labeling the points and write down an approximate value of k. So we have to identify obviously which one is Z1, then Z2 is going to be IZ1, so let's make a note for ourselves. So that's a 90-degree rotation. Which way? That's going to be anti-clockwise. A 90-degree rotation anti-clockwise. So that suggests to me that Z2 might be either of these two ones here, if Z1 is either of these two ones. Because if we want to rotate anti-clockwise, then we have to have Z1 on the right-hand side to rotate to the left-hand side. We note as well that there shouldn't be any difference in how far it is from the origin. Z3 is going to be KZ1, where K is an element of OR. So we're noting that K is not necessarily going to be a whole number. It could be a fraction. It could be a fraction smaller than 1. So it could be a stretching or a kind of reducing, if we like. So let's just make a note of that. So it could be a stretch or it could be a reduction. Okay, a kind of compression, whatever words we want to use. Kind of, we could be stretching it further out, we could be making it smaller. Then the last one, Z4, is Z2 plus Z3. Z2 plus Z3. So that one's going to end up being between wherever we decide Z2 and Z3 are going to be. Okay, so let's try and work these ones out for ourselves, I suppose. So say I start with this number out here. So we know that Z3 is going to be one of these two, depending on the value of k. If we look at this example, this complex number out to the left-hand side here, the two that I've joined up are making a 90-degree angle with each other. And when we're doing that rotation of I, we made a note as well. We said to ourselves that it hasn't been stretched or anything. We haven't changed how far it is from the origin. So from looking at that, I would say that this number must be Z1 and this number must be Z2, because they're a similar distance from the origin. We haven't changed that distance and they're making a 90-degree angle with each other about the origin. So they've gone through a rotation through the origin there. Then if we're looking at Z3, well, we've said that Z3 had to be either of those two, so Z3 must be this one here, which suggests to us that K must be a fraction to have made that value smaller, to have made Z3 closer to the origin. That's going to mean then by process of elimination that Z4 is going to be up here, and we can kind of see for ourselves if we connect those values to make that parallelogram, like we said in the previous section, we do end up with Z4 being the corner of the diagonal there of that parallelogram, as we kind of have expected there. So that's perfect. And the proximate value of k, I would say that k there looks to approximately be a half, that z3 might be half as far from the origin, or half the distance that z1 is from the origin. Looking then at the last section, this Argand diagram shows the complex number u. Write the complex numbers iu and the conjugate of iu in their simplest form. So let's work out those numbers first. Iu is going to be ai plus bi squared, which is minus b plus ai. And the conjugate of that then is going to be minus b minus ai. We're going to plot and label the complex numbers on the diagram above. Again, we don't really have any kind of scales or anything for ourselves, but we can kind of use our logic here. So IU should be at a 90-degree angle. So we would use probably a compass or we could use a compass at this point, or not a compass, a protractor, to get our 90 degrees here. And we could use a compass maybe about that point to ensure that we keep these numbers being at the same point after the rotation. So if we put our compass point here and then draw a little arc from that point to this point, keeping the distance the same until we get that 90-degree angle, that will give us that 90-degree rotation. But we've got our general idea here. Again, I'm plotting it as accurately as I can on my iPad here. So we've got IU, and then the complex conjugate, we should know the complex conjugate is a reflection. It's going to be a reflection of our complex number in the real axis, because all we change is the complex part. So we plotted and labeled those, and then stated a series of transformations that would send u to the conjugate of IU. And I would say that that series of transformations is a rotation and then a reflection, as we've said there. So a rotation and then a reflection in the real axis. So those are kind of our key things with our complex numbers there and our transformations. And there is a fair bit to go over, and you can kind of see with those questions there, like when they do come up, you do have to have a fair understanding of what's happening in all those points and what does it mean to multiply by I, and how does it look if I'm adding the numbers or if I'm subtracting, and how can I kind of help myself identify those numbers. So it is one that's worth just kind of spending a little bit of time on to make sure that you have some idea or some sense of what all those transformations represent.